Let's look at the recurrence part first. All right. So we have this diagram from C.3. From this diagram, how can we get the recurrence relation? Here, let's define an S function. What is this function? This one we call it the cost function. The cost for what? The cost for the whole selection problem. Okay? And so what is this M? The problem size, right? The size number. And so to solve a selection problem of size n, we need to pay this much cost. That's the definition of this cost function. Let's derive a recurrence relation for this cost function. All right, yeah. Let's do here. We estimate this cost function. This cost function can be estimated using several terms, because when we do step by step, each step we need to pay some cost. Let's look at the first step, the cost we pay. The first step, we need to pay the cost n comparisons. Why n comparison? Look at this. N equals 3R, right? When we find the medians of all our groups with 3 elements each, how many comparisons do we need? For each group, we need 3 comparisons. But we have R groups, right? So the total number of comparisons we need to find all the medians for the R groups. R groups, that is this cost, n comparisons. That's the first term. The second term. The second term, when we look at the second term, look at this, the S. 2S approximately equal n over 3. Yeah. From here, yeah, because 6S plus 3 equals n. So 2s approximately. Yeah, there is some small fraction. Yeah, so we can drop it. Yeah, 2s comparisons. Remember, for A, B, this part in the middle, we need to do 2s comparisons. Okay, that means we need to do 1/3 of n comparisons. So that's our second term. That's another cost we need to pay. Right? Then the third term, another cost we need to pay when you find the median of median. Median of medians, the M star, how much cost do we pay? How many comparisons do we need to pay? That is another selection problem, right? The selection problem. What is the size of that problem? N over 3. The R, the size R, so that is the cost we need to pay. Okay? So that's why we have this S of n over 3. Okay? All right. So the last term, we need to pay the cost, S of 2n over 3. Why 2n over 3? Okay. Look at after the partition. All right. After the partition, we drop one subarray. Then there is a remaining subarray left. What is the size of the remaining subarray? Right? So the size is this. Okay? Remaining subarray. For example, could be this subarray, could be that subarray, right? The maximum possible here, I'm sorry, not that. Okay? So here, another possibility is this, right? But the question is, what is the maximum possible array size? maximum, because maximum corresponds to the worst case, right? Worst case. We need to consider the worst case. The maximum possible size, this B covers, everything. Okay? All these 2S elements are greater than M star. Okay? So in that case, the subarray that is dropped only about 1/3 of the original array. So we drop 1/3 of the original array. The remaining 2/3, we need to do another selection problem. That's why we use this estimate, because that's for the worst case, right? So here we will consider worst case. The worst case, we will pay more cost. Okay, we will pay more. Yeah. So that's here we use inequality. So we have no problem. Okay. So this inequality is correct. We have no problem. Okay. All right. So that is the, this recurrence relation. Okay. But we also need the base case, S of 0 and S of 1 both equals 0. Okay, no cost. No. From that, now let's simplify. Yeah, so simplify the inequality a little bit. So we derive the recurrence relation. Although it is an inequality, but we can still solve it. So our next problem, how to solve this recurrence relation as an inequality. So the next slide, we will solve it. This is our current problem we need to solve. Okay? In this slide, I want to introduce a special method called recursion tree method. This is a very nice method. So I want to introduce to you, very useful sometimes, especially for this situation. So let me draw this tree, recurrence tree. The tree is based on the recurrence relation we have here. Okay? All right. Let's start from the root. The root, we want to estimate S of n. In order to do that, we look at the right-hand side of the inequality. Okay? What do we need to do at the right-hand side? First, we need to solve two subproblems. Okay? So here, you need to pay the cost, but for two smaller subproblems. Okay? Other than that, you need to pay another non-recurrence cost. This is non-recurrence cost. 4n/3, the non-recurrence cost. All right. But for each S function, you need to keep doing recurrence calls, and you also need to pay some non-recurrence cost every time. Okay? All right. So now, the next time when we do recurrence calls, two recurrence calls, we pay two terms, non-recurrence cost. What's the total? Let's add them together. Another 4n/3. Here you can see the same, each level the same non-recurrence cost. If we go another level, we get another 4n/3. So we keep going. Every time we pay the same amount of non-recurrence cost. So the question is, how far we can go? How many levels we can go? We need to estimate the number of levels. All right. The number of levels based on the structure here, because every time we do some division, right? So this side we do division by 3 every time. That side we do division by 3 over 2. Okay? So the number of levels related to the log function. Okay? Log function. Multiply some constant multiple. We may need to multiply certain constant multiple, but the main function is the log function. Okay? That's the number of levels, log function. Yeah. So now you can see the total cost we need to pay. Yeah. Each level we pay constant times n, right? Certain constant times n. So that's the n part. Number of levels, another constant times log of n. So finally, some constant times n log n. So our S function is in this category, big theta of n log n. The problem is with this growth function, are we happy? Right? So are we satisfied with this result? Right? Definitely we're not satisfied. Yeah. Our goal, we want to get a big theta of n. So we want this performance. That means this method, although we spend a lot of time, a lot of effort, it does not work. We need to improve it. We need to find a better solution. Okay? So the improvement idea, use 5 element groups. Remember our current method uses 3 element groups. Can we do it over again, but we use the 5 element groups? Okay? So that's our last piece of this lecture, C.5. We will use this method to solve the selection problem. All right, let's stop here.